Welcome. Uh, in the previous video, we learned about Darcy law, and we learned that you have a hydraulic gradient, and then you have a hydraulic conductivity, and this hydraulic conductivity and hydraulic gradient, this will determine your flow or your specific discharge. Okay. So in this video, uh, so it was something like this. Yeah, remember, like in this video, we will learn about like how to measure hydraulic conductivity. So remember, we had something like this: Q is equal to Ki. This is the hydraulic gradient, and this is the hydraulic conductivity. So in this video, we will like as we go through this course, we will keep learning more and more about like this hydraulic conductivity, and because that's a very central concept in the groundwater hydrology, yeah, and also in surface water groundwater interaction. Yeah, that's like a central topic. Okay, so we will by so the end of this video, you should be able to describe like typical ranges of value for hydraulic conductivity. So remember we talked before about something like clay, sand, gravel, and different like type of sediments or even different types of rocks, not necessarily sediments. So in this video, you will describe like you will know like what would be a typical range for hydraulic conductivity for sand or versus gravel versus clay, for example. And we know that this would be like much higher than this, and this would be like not higher. This would be higher than this, and this would be much higher than this, for example. Yeah. And then you should be able to explain like different laboratory method for measuring hydraulic conductivity. So how to measure it? Like what we learned before is like the hydraulic conductivity, yes? Like what is hydraulic conductivity? But in this video, you will measure like we learned Darcy law, for example, and from Darcy law, we learned about hydraulic conductivity, yeah? But in this video, we'll learn like how to conduct Darcy law or how to measure this hydraulic conductivity, like similar to what Darcy did in his Darcy experiment, for example. Yeah. So we'll learn like three different laboratory method for measuring hydraulic conductivity, three different experiments, and then we will briefly discuss like field method also for measuring hydraulic conductivity, because we will this field method we will do later in the course. Yeah. Okay, so again, that's like your social media or Facebook activity for this lesson is similar to other lessons also. So that's your participation activity. I think that should be part. I think this is a typo. Here that should be number 3. That's your participation activity number 3. So just correct this typo. Yeah, because this is the third lesson. The first lesson was about like porosity, and the second lesson was about Darcy law, and this is the third lesson about measuring hydraulic conductivity. Okay, so here we go. So this video, for example, like remember hydraulic conductivity? Let's look at Darcy law again, like Q is equal to K I. I, this is like delta H over delta L. So this is like a unit of length. This is a unit of length. So I is, sorry, I keep saying units. This is dimensions. This is dimensionless. And Q, remember Q, like Q, big Q is equal to small q times A. We know that this big Q has a L over T, and this A has L squared, so the small q would be like L over T. So we know like that this guy has a unit of L over T. So what would be the unit of this guy? So the unit, like this is dimension, sorry, I keep saying units, like the dimension of this guy is L over T. The dimension of this guy is dimensionless. So what would be the dimension of this guy? So the dimension of this guy would be L over T. Yeah, to achieve dimension homogeneity. Uh, okay, so let me do this. So we expected, so that's the dimension. It is like L over T. Yeah. L over T, that's the dimension. But what could be the unit for this? The unit for this could be, for example, L could be in meter and time could be in second, or L could be in meter and time could be in day, or L could be in millimeter per second, or whatever. Yeah. So here you see like uh, this is basically how to convert like different values for hydraulic conductivity. So for example, like 1 meter per day, that's about this number per second, yeah, and 1 centimeter per second, that's about like 1 gallon per day per feet square, yeah. So if you want to use this weird unit, yeah, uh, 1 centimeter per second, for example, is like this feet per day. So you have like the dimension, you have the unit, and then each unit it has a unit convention, like whether you are using like SI unit or whether you are using like imperial units or whatever. So in the USA units is like in feet per day, so hydraulic conductivity could be measured in feet per day in hydrogeological practice. Centimeter per second, this is used like for soil scientists, engineers, so they will use like centimeter per second. In SI system, the units for hydraulic conductivity is like meter per day. So that's like the SI system. You expected like meter per second, but actually it is meter per day. And then you can drive it unit of gallons per day per square feet was used in the past. So these are like units that were used in the past. So if you saw this unit, don't just say, "Oh my God, what is this?" Yeah, these were just like a unit that was measured in the past. But hydraulic conductivity, it has like several order of magnitude over different like geological materials. So that's what I want to show you here. So here, this is the value of intrinsic permeability. And remember, like intrinsic permeability, that's like in Darcy, it has a dimension of L squared. So that is in Darcy, whatever that means. And so that is a property. Remember, yeah, intrinsic permeability, that's a property of material. Hydraulic conductivity, that's property of material and fluid. So we assume here that is like fresh water, okay? So you see here, let's look at hydraulic conductivity value because these are like permeability value are not commonly used, like what you will commonly read in like literature and reports and things like that is like value in hydraulic conductivity. And they could have a unit of SI unit like meter per day or meter per second or like in soil scientists, as I mentioned, that could be like centimeter per second or whatever. But let's look at these ones and uh, so for clay, for example, you see it's very small, like, and this is in centimeter, not even in meters. So if in meters, that would be even smaller. So clay, the hydraulic conductivity value is like very small. Silt, sandy silt, clay, sandy till. So these would be like if you one day will be analyzing driller logs. So when you go for drilling, for you drill like a well, whether this is a monitoring well, whether this is a pumping well, whether this is an injection well, there would be the drilling company or you as in you will be logging like the different materials that you will see. So some of these materials that you will read on this drilling log, you'll read like silty sand or clay sand or till, and this is something that has a very low hydraulic conductivity also. And then you can read something like silty sands, fine sands, and this something has like a little bit higher like hydraulic conductivity. But then you will read something like well sorted sand, glacier out. So well sorted sand and glacier outwash, this will have like higher hydraulic conductivity, and well sorted gravel that would have like the highest hydraulic conductivity. And that's, remember, this is in centimeter per second. So if that is in meter per second, so that would be like 10 to the power minus 4 to 10 to the power minus 2. Yeah, that would be for this one. For sand, like a typical value for sand, 10 to the power minus 3 to 10 to the power minus 5. That's like in meter per second, meter per second. So yeah, sand usually is around this number. Yeah, and then so that would be pervious. Up till here, that would be like silty sand, or well, I mean, or you can think like this is pervious. and we will learn this is like an aquifer. So this form a good aquifer, this form a good aquitard, like impervious material. Especially like here, that would be like a confining layer or an impervious material, as we will learn later. But just keep these values in mind, yeah? Okay, so here is the hydraulic conductivity of selected rock, and you would find here different scale. Like this is all the scale, like gallon per day per feet. This is feet per day. This is, and this is meter per day. Like so, this is scale like is SI unit. Okay, so this is the important one. So just focus on this one. Like these are not very important. So focus on this one. Like this is the SI unit meter per day. So these numbers are in meter per day. So like let's look at something like igneous and metamorphic rock. So igneous, these are volcanic rock, and that is similar to like the basalt that you find in Hawaii, like basalt. Basalt is this black rock that you find in Hawaii, and you see it has a very big range of hydraulic conductivity. That's like in meter per day. Uh, so from very impervious to like very pervious, similar to like sand. So like you see here, it goes like similar to sand, like to coarse sand, like medium to coarse sand. And that's why, because that's depending on fracture. So if you just have a piece of rock, solid rock, a basalt, if it's unfractured, it has no fracture, it's just a piece of solid rock. Its permeability or its hydraulic conductivity would be very low. But once it starts, like you have fractures in it, where water can flow, so you have like these fractures, yeah, and where water, uh, where like you have uh, these fractures, yeah, see, where water can flow here, can flow here, can flow here, then it will start to have good permeability. It will start to be good good conductor for water, yeah. Uh, so that would be like a good conductor for water. Yeah, like so that's high permeability. That's similar, by the way, to Ohm's law. Like, do you remember like Ohm's law for electricity? V is equal to RI. Voltage, the potential volt is equal to uh, resistance time current. Here, like in groundwater, it's a similar way. Like, so you can write it like H is equal to so here, let's see. Like this is like you can just write delta V here and delta H over like you can just write I here. Like the hydraulic gradient. You can leave it here. So like remember, like Darcy law is something like this: Q is equal to K I. So you can write it also I. So that's the potential different, and that is a gradient different. Yeah, like so that's the potential. Both are potential, and this potential will cause like current to flow. So this potential will cause like your groundwater to flow, and so Ohm's law. This is our Darcy law. That would be like 1 over K, because conductivity is opposite, like is the inverse of resistivity. So that's Ohm's law for flow of current, and that is Darcy law for flow of groundwater. So here you have your flow, your flux. Here you have your current. Here you have your potential. Here you have like that's the hydraulic potential. That's the electric potential. Here charges are flowing. Here groundwater are flowing, and then here you have resistance. This here 1 over K, which is uh, conductivity, which is the inverse of resistivity. Okay. So you can just think about this. So hydraulic conductivity basically tell you how good this is conductor for water, how good water flow, just similar to electricity, how good electric current will flow. And it's similar, like, in electricity, if you have the wire is thicker, bigger diameter, you will find more flow of current. Similarly, in groundwater, if you have a bigger cross-sectional area, you'll find more the flow of groundwater. But anyway, this is just an analogy to better understand like the term hydraulic conductivity. But it just tell you how this is good conductor for water. So if you have a solid piece of granite, this is not a good conductor of water at all. So you have very low hydraulic conductivity. If you have a high value then this is a good conductor of water, and this is hydraulic conductivity. So here, this is like a basalt, which is a type of like a igneous rock. So here, this is unfractured, this is fractured, and this is lava flow. So lava flow that has a very high hydraulic conductivity, similar to gravel. Yeah, so that's a good conductor of water, because you could have channel like similar to like this karst channel, and you can have something called vugs also. So you have like something. So in these things, you could have like channel similar to karst channel, but then you have vugs. I don't know how to draw the vugs. So let's say it's like vugs are like kind of a channels where water can flow also in them, something like this. Yeah, on a micro scale, like not on a bigger channel like as a cars, but like on a small scale. Okay, now sandstone, you see it has like this is fractured and semi-consolidated. So sandstone, like this is a fracture of this is a semi-consolidated, like you don't have much consolidation, then you will have more hydraulic conductivity. So these are with like, so these are sedimentary rocks, these are igneous. Metamorphic rock, that an example of a metamorphic rock would be marble, for example. That would be an example of a metamorphic rock. Yeah, marble. I think so. Yeah, okay. Shale, so if it is fractured or unfractured, it will still have like a very low hydraulic conductivity. So you can use like this sand here as your, you know, like, as your, let's draw this, like you can use sand here as your, so that will make a good aquifer, and where water can flow, that will make a good like confining layer or aquitard where water will not flow. Yeah, generally speaking. Okay, so now you see here like carbonated rock. So carbonated rocks, that's like karst, like the karst we have here in Florida. So carbonate rock, again, if it's fractured or unfractured. So young karst will be unfractured. You'll just see again a piece of uh, of of rock, solid rock, yeah, a piece of solid rock, but once it's mature, as we saw like in the previous image where you have the solutions, then once it has the solutions, then some cracks will open, so you'll see some cracks. Yeah, you'll see some cracks, and then with time, these cracks will grow and will form like not just some cracks, but will form like conduit, like a big conduit, and even a cave, like a big cave. And that will basically, like if you have a conduit, for example, for a carbonate rock, that's even Darcy law will not be valid here. Then you can use Darcy-Weisbach equations. That's like an open channel flow, or even if it's saturated with water, that would be like a pressurized flow. Yeah, because that's flow in a conduit, not flow in a matrix, not flow in a porous medium. Similarly, we talked also about this when we discussed like secondary porosity. When you have fractured, also Darcy law does not apply, and we use something called the cubic law for flow in fractures. But anyway, um, so silty sands, that's again the hydraulic conductivity. So maybe, yeah, starting from here, you started to have an aquifer, maybe starting from here. Yeah. So starting from here, you start to have an aquifer, like a little bit of silty sand and little bit of glacial till and clean sand and gravel. But here, glacial till, these can be very heterogeneous. So glacial till, because they are formed of composites of materials, and they are generally not well sorted. They are poorly sorted because, yeah, composite of material, and that's why it could be very like heterogeneous. It could vary orders of magnitude. Like you see here, it's varying like 6 orders of magnitude. Yeah. Here, like sand, like it depend, like coarse sand, like this is a clean sand. So if it's fine sand, it will has less hydraulic conductivity than a medium sand, than a coarse sand, and gravel that would have the highest hydraulic conductivity, because gravel, these are big particle. You generally have very good and connected flow passes, because you have this big particle and you have very well and connected flow passes. Okay, so these are the values of hydraulic conductivity. So let's look at typical values. So maybe we can, you just like, you don't need to memorize it, but you just like, so just for, because these are just common knowledge that you, as a practicing groundwater hydrologist or water resources engineer, It's always good to have this type of knowledge. So for the hydraulic conductivity of a fine sand, that goes like all the way from like uh, 10 like uh, 0.01 to coarse sand like mm, that's like 100 meter per day. So like from zero point zero 0.01 meter per day to 100 meter per day. Like a silty sand, see, it is a little bit like smaller. So like you can consider this like, I don't know, point zero 0.05. Point zero 0.05, that's like 5 centimeter per day, yeah, to mm, that's like from like to 10 meter per day. That's like the K value for this one. Gravel, it could goes up to, and like see cars conduit, it goes up there. And see here in Hawaii, like in when we do like modeling here in Florida, we can conceptualize this car system as a porous media, and then we assign a very high hydraulic conductivity, and then you would see like this very high value, like unusual value, like 10 to the power 4 meter per day. This is very unusual for groundwater because groundwater you expect something like this. Like you expect typically, just like see from that's the value that you will expect. You'll expect something like this, maybe 1 meter per day, 10 meter per day, but not 10,000 meter per day. That's very high. But here in Florida, remember when I was talking about the Pesican aquifer? So the Pesican aquifer here, we have a model for it. We are using it to study climate change impact on on in South Florida. By the way, this could be like remember your final project for this course, it could be either like the standard project that I'm giving to you, or you can make your own project or have your own topic. So that could be like you can use these models that we have for the Pisican aquifer, and you can use to study any process that is of interest to you, including like impact of climate change, some mitigation measure for the impact of climate change or whatever you want to test. So you can use this model. But anyway, so if you start using this model, you will find that the hydraulic conductivity value in this model are very high, like something 10 to the power minus 4. And you're going to say, what? Is this true? Or this is something wrong here? Yes, it is true because this is a carbonate rock with a mature karst system like we have here in Florida. That's a mature karst system with conduit, with fractures, with um, it's a wet karst system also. So we have this like you expect like to have like point 0.1 or 1 or like 10 or even 100 meter per day, but like you get 10,000, and this is true. And even like you could even find like values like 17,000 like meter per day. I think I don't remember, like don't quote me for this, but maybe we also could have like the value something like this, like 17,000 meter cube per day or things like that. Okay. So just keep these numbers in mind because that would be like your common sense or your engineering sense. Remember, the most important thing in engineering is that you, as an engineer, and as you keep learning, you develop an engineering sense. And part of this engineering sense is to have a sense of like how conductive or non-conductive like different material would be. Okay, so here this is another figure. So I will not do this one in details because I will not do this one in details because it's just similar to another one. But here you find this like when I learned it, this thing, the units that were mainly using was meter per second. So that's why. So you can just like develop. So I know, for example, like sand is like 10 to the power minus 3. Gravel or silt, sorry, like silt or clay is at 10 to the power minus 6. Gravel would be something like this. So that's how I know it. That's when I learned it. Yeah, I know like some igneous rock that would be like not pervious at all. There will be no flow here. Like 10 to the power minus 13 meter per second, like or 10 to the power minus 12 or whatever. Like these numbers, there is almost no flow here. So here in this region, like no flow or almost no flow. Yeah, almost no flow. Here, very like in this region here from 10 to the power minus 5 to 10 to the power minus 4, very like small flow or slow, very slow flow or very small flow, small slow flow. And here you have like it's a good hydraulic conductivity, good flow. Yeah, for from anywhere from 1 and to this one. So just pause the video and read like this one and like try to make sense with these numbers. Okay. One more thing, so this also another important concept that you should know, that porosity has nothing to do with hydraulic conductivity. So you can have very high porosity, like clay, for example, it has very high porosity, but very low hydraulic conductivity. Why? Because you have a lot of pore spaces that are not well connected, versus gravel, it has a very low porosity, but the highest hydraulic conductivity. Yeah, so that's something, and that would be in the exam. Like, and I will put a big grade on this one because this is one of the most important concepts as a water resources engineer you need to understand, because this is not only important for groundwater, this is also important for flooding. Like if you're studying flooding, you need to know the porosity and like the or the hydraulic conductivity or the porosity and different material, because this one, for example, will cause flooding. Like if your topsoil layer is clay, that will prevent infiltration and thus would have more susceptible for flooding, versus gravel and sand that would be less susceptible for flooding. So here less flooding, yeah, while here like more flooding, for example. Yeah. Okay. uh, so that is one thing you need to know. And then we talked also about specific yield, and remember, like specific yield, this is drainage by gravity. So let's say I have like a column here that is full of like gravel, for example, and then I have a screen here, and then I open the screen and let water flow by gravity. So specific yield of clay and silts is very low, because most of the water particle will be like in dead end pore, so they will not, or like stuck on the clay mineral or in dead end pore, so they will not flow and will not drain. So you get like very low draining. You get usually the highest draining would be with sand, that is like, or like a little bit of gravel, like small gravel. And but you see here, when the gravel become bigger, then the specific yield drainage will be a little bit less. And do you know why? Like remember, I told you why. That's mainly due to surface tension. Like so, that's not due to dead end pore, but that's due to surface tension. So like you have a big gravel site, so you will find like water film on here on the surface. So you will find the water film here, maybe like another water film here, and that will not drain by gravity. So that's why like sand and like fine gravel, that you will have like the highest drainage, while like coarse sand, because this is like will be like your clay, like your gravel or boulder or pedals or whatever, and on the walls of this you will find like a water film. Okay, so now let's this important slide, because remember here, let's look at our Darcy law again. Q is equal to negative Ki. I told you groundwater is the easiest thing you can study because you only have one equation. But look at this. This is K. So so here this is like a small, like you see this is on a centimeter scale, and here this is on a meter scale. And this is the scary, like see at a centimeter scale, see how hydraulic conductivity, this K value varies. So here like you have clay. Here you have well sorted and coarse and well sorted coarse sand. Here you have poorly sorted mixture of gravel and sand. On just a small, like on a centimeter scale, like see this is pencil. So this like on a centimeter scale. See how heterogeneous the subsurface could be. And that's why it is like groundwater modeling could be challenging, because we try to define this hydraulic conductivity field in the subsurface, and the subsurface is something we cannot see. Like this could be an outcrop or a sample that was extracted from the subsurface, but the subsurface is something down there. And as a As a hydrogeologist or water resources engineer, your job is to reconstruct like this subsurface. And because like once you construct like this subsurface, we construct like different hydraulic conductivity, the hydraulic conductivity field or different hydraulic conductivity zone, then you will be able to model your flow, because the flow in each of these one is different, including the flow velocity. And if you are doing contaminant transport, that would be also the transport of this contaminant will be different. Because so your job would be to reconstruct this image, and that's what we will learn in this course. So in this course we will learn like different technique for like reconstructing like an image that looks something like this. Yeah. So in this video, which will be measuring like looking at hydraulic conductivity, we will mainly look at like centimeter scale or like sample scale. Like, so you take a sample like this, so this is like a sample. So this is a pencil, so this could be like, I don't know, like maybe 20 centimeter by like 20 centimeter or whatever, how big that is, 30 maybe centimeter or by 30 centimeter. So you take like a sample like this, and then you measure it in the lab, and then you will estimate like the average hydraulic conductivity for this sample. Yeah. And of course, like it, that would be directional dependent also. Like if you put the sample in this direction versus if you measure hydraulic conductivity from this direction, yeah, that could be directional dependent. So depend, and we will learn about this later when we get to groundwater flow equation. But for now, I just want you to keep this in mind. Now, this is at a different scale. So now, let's say I will measure this hydraulic conductivity. I will not find like the value for the K for like 1 here and K2 here and K3 here, but rather I will find like a K average for all these guys. Yeah. I'll find like an average K for all these guys. So maybe like if you look at this, the average K might be something like this. So that could be this zone. So at a larger scale, if you are looking at a meter scale, then see how heterogeneous your subsurface could be. So nature is somehow like harsh or challenging for water resources engineer or like groundwater hydrologist because of heterogeneity. Yeah. And but like for this, like how to do this, we will learn like in this video, we'll learn some laboratory method to find this at like small scale, but later in the course we will learn field method, and there will be also field trip where we will learn how to do this at a larger scale, okay, with the field trip. Okay, and you can learn more about this field trip, like the details of this field trip would be on campus, yeah. Okay, so before we start our lesson, and so our main lesson here would be like to learn how to find hydraulic conductivity in the lab scale. So lab scales have to be a small sample, like so the sample could be, I don't know, like 30 centimeter by 30 centimeter, 20 centimeter by 20 centimeter, whatever how big your sample is, or 30 centimeter by 1 meter, or however how big your sample is. So that's what we learn in this video, and later we will learn in other courses we will learn this. But before we do this, let's just do review. I just want to make sure that these concepts are clear to you and that you can understand this concept very well. So here, for example, I'm asking you, what is the porosity range for well-sorted sand or gravel? So I want you to pause this video, get like your lecture notes. So that's like here. Let me show you. So that's like your this card. That's like your lecture notes. So like if you go here, like to the porosity lesson, which we did, and then you can find like these answers here. Uh, let's look what are the other questions that I'm asking here. Oops, what are the other questions? Let's look here. What is the permeability? What is primary porosity, and what are controlling factor of primary porosity? So primary porosity is as the porosity of your porous media. What is secondary porosity? So remember, secondary porosity is as like porosity that happens after the sedimentation or after the formation of your sediments. So the sedimentation already occur, or like the deposition of these geological material already occurred, and then after the deposition, then some secondary porosity will start to open, like fractures, like dissolution, which will cause like karst conduit and cave. So try to go back and answer this question. And what are the units for hydraulic head? hydraulic gradient, and Darcy flux, like specific discharge. Like so, let me make this one specific discharge. Oops. Let's go here. In color, I like to use this color. So specific discharge, that's like Q. So hydraulic heads, that's H. Hydraulic gradients, that's delta H over delta L. And Darcy flux or the specific discharge Q. Okay, so please review this before we move forward, because one challenge of this course is that you will find a lot of terms like hydraulic head, hydraulic gradient, Darcy flux, specific yield. Yeah. Porosity. So so I want you to, that's again to develop like your engineering sense. I want you to master this basic concepts and this basic definition, because these are very basic definition for you, like as a water resources engineer or as a geotechnical engineer or as structure engineer who's designing foundation. Because if you are a structure engineer and you're designing foundation, you need to learn this, because you will need to see where your water table is, and then you need to do dewatering. You get some pumps and do dewatering, and we will learn this, like we have, like this is a module, like not the next module, but the module after, like well hydraulics, like how to pump water and reduce like your groundwater table, and or like dewater like a site or something like this. Okay. Okay, so please learn these. These are basic concepts that I want you to master before we move forward. But okay, so pause the video and do this. Okay, and come back. Okay, so welcome back. Now we will remember, like we talk about like hydraulic conductivity, how to measure hydraulic conductivity. So we will look at 3 laboratory methods for measuring hydraulic conductivity. And to measure hydraulic conductivity, what you do, like you go to the field, you get the sample, and you take it out to the lab, and like you measure it in the lab. So one of the uh, method is like called like grain size analysis, and we looked at grain size analysis. So this is called like the Hazen method, and the Hazen method is very simple. It's basically tell you like look at effective grain size like D10, and we learned it before how to find D10, like square it and then multiply it by some shape factor. So this is an empirical constant depending on the shape packing of the sediment grain. So C range from 40 for a very fine poorly sorted sand to 150 for coarse, clean, and well sorted sand, for example. In addition, the above equation, there are many others. So this is just one empirical formula, the Hazen equation, but there are so many other of these like empirical formulas that was developed like after Hazen equation, so that's the good news is that it's very easy to do, like to measure hydraulic conductivity in this way, because like if you are doing like a grain size analysis, that's an easy and standard test. Like in any construction site, they always do this, like in the lab, in any many, not any, but like many, especially in big projects, they're always doing these things. And so it's a very, very standard test. Yeah. And once you did this standard test, you find like your D10. So if you are doing like in a construction site or like in a project and you want something quick, just get your D10 multiplied by this shape factor, depending on like on your knowledge of the material, and then you will estimate the hydraulic conductivity. So it is fast. So the good thing that these methods are fast, but they are not accurate. That's the bad news, is that they are not very much accurate. Okay, so here we did this example before, so I will don't want to like, oops, I don't want to spend much time here, because we looked at this, we looked at this before. So remember, like this is your sieve size. You go and at each sieve you find like the percentage that was retained in after like you do your sieve analysis, the percent that was retained in this sieve, and then you plot it, and then you find your D10. Oops. And then you find like your D10 here. So like, for example, the D10 will be like the percent like finer by weights and 10%. That would be your D10. And then you read the grain size, and that would be according to Hazen, that's the effective grain size. So in that case, for example, like if you want to read this number here, so this is 0.01, this would be like 0.02. So that's something here between 0.01 and 0.02. It's usually like it's more on this side. You might say, oh, so it would be like 0.0, like 1.8 or 1.9, but actually it's not, because remember the log scale is non-linear. So if it is close to here, that doesn't mean it's 0.18, it might be 0.16, because this is non-linear. This is a non-linear scale, so it does not, you cannot just divide this by distance. Yeah, so here that would be still to find medium sand. Here it will be like a fine sand, so this would be have more hydraulic conductivity than this one. And then, so basically this is the C, and like you check if a table that looks like this. Uh, so here, based on like, so this is here like silt or clay, sand like coarse, medium, fine, gravel, coarse, and medium. So you find the D10 size, and then after the D10 size, you check like which category you fall in. So you get like a number here. And again, it could be any number between like, so you just try to see where you are here. So like if I'm here, then it would be like fine sand with appreciable fire. So maybe your C value would be around like 60. Yeah. And that's why it's so unclear. Yeah. Like, am I going to choose like 40 or 80, or maybe I will choose something around 60. But anyway, uh, so for your laboratory test, that's basically so here, like I want you to do this example, and that would be like similar to your homework. So please read this example and do it. That is similar to your homework. It basically say use the Hazen method to estimate the hydraulic conductivity of sediment in this graph. Determine the effective grain size and uniformity coefficient of the sediment in the graph. Okay. Uh, so the uniformity coefficient, we did this before, yeah? So that's the uniformity coefficient, that's D10 over D60. So I'm not going to do this, but it tells you here, use the Hazen method to estimate hydraulic conductivity. So the hydraulic conductivity, that would be the D10 square. But again, the most difficult thing about this one is how to read this value accurately from the graph. So like you stretch a line here up till here, you hit this point, and then like you see this point here, this is my 0.1. Oops, my 0.1 here. This is my 0.2 here. Don't be fooled and say, okay, this is close to the point 2. Sorry, this is close to this point 1. This is point 2. Don't be fooled and say, oh, and say this is close to 2, because this is a non-linear scale. So this would be like, if I would say like my D10 in that case would be about 0.016 millimeter. Okay. Be careful, like you need to convert this to like centimeter, or like, yeah, like to get like your hydraulic conductivity in centimeters. This is in centimeter, so you convert like this to centimeters. So that would be like if you converted this value to centimeter, uh, so that would be so this is like a millimeter. Sorry, not in meter. This is millimeter. I have a typo here. So this is millimeter, and so 10 millimeter, oops, millimeter is equal to 1 centimeter. Okay, so if I want to convert this like to centimeters, so that would be 0.001 like centimeter. Okay, see, yeah, so that's basically like how to do this. So try to solve it now, like try to plug it here and try to find like now see, this is about what? So this is about like the grain size. This is about sand, like a fine sand. So find the C for a fine sand and then calculate K. So try to do it. I'm not going to do it. Try to do it, and after you do it, you can check your answer. So always like remember, in all these slides, I post the correct answer here at the bottom. So you see. So try to do it and then try to find like what type of sand, like is this like well sorted or poorly sorted, and this is you get this from the uniformity coefficient. But don't look at the answer, just solve it yourself and then check your answer once you are done. Yeah. Okay, so this is the answer, but don't look at it, just solve it yourself, and after you solve it yourself, like you can check the answer. So always look at the notes down there in this slides and where you will find the answers for this problem. Okay, so that's one method for estimating uh, for uh, estimating hydraulic conductivity, and it's not a very accurate method. Another method, guess what, would be to like conduct a Darcy experiment. Just do similar to what Darcy did, and this is called like constant Herb permeameter. And I think this constant Herb permeameter, you did this already in the geotechnical engineering class. So I think this is maybe one of the experiments that you do in the geotechnical engineering class. So I will just I'll explain it quickly. But so remember, like here you have this is again you want to maintain the head difference between like your uh, inlet and your outlet here to be constant. So how to do this? You just put a constant supply of water. Any excess water will flow here, and then you will maintain. Oops. And then you will maintain this level here. Yeah, you will maintain the water level here, and then any excess water here will flow here, and then you will maintain this level here. You put a screen here, and you put screen here so that like your sand will not fall out of your experiment. Yeah. And basically, so now, and then you just use Darcy law. Yeah, remember Darcy law? So Darcy law, we have something like this: Q is equal to negative K A I. Yeah, and what is I? I is like delta H over delta L. Wow. Okay. So what is delta H here? That's like delta H. Yeah, so that's like delta H, which is constant because that's exactly what you do. Like it's a constant head. And what is delta L? That is your flow. So that's like your sample. So that's where the sand, where the water will be flowing. So water will flow from here, yeah, till here. So that would be like your delta L. Yeah. So that would be like, so delta L, that would be L. Yeah, this L here. That's your delta L. Okay. And what would be your A? What would be your area? So your area, that would be like the diameter, if this is like a cylinder, so the diameter of this cylinder, and then you can calculate the area of the cylinder where water is flowing. Yeah. So what do we know? Like we know the delta H because we already like this is delta H. So this is the head here. So at my first reservoir, this is H1. At my second reservoir, this is H2. And my delta H would be like H2 minus H1. So I have this. So this is known. My L, the flow length through like the porous media, this is known. The area of my cylinder where the sand, the sand column where the water will be flowing. This is known. And what do I want? This is what I want to estimate. But do I know Q? Yeah, because water is outflowing here, so you can basically measure how much water is flowing here. And you can usually simply do this with like a stopwatch. Yeah, so you have like a beaker here or whatever, something where you can measure the amount of water, and then you have a stopwatch. So remember Q, that is like volume over time. Yeah. So basically, like at each amount of time you measure the velocity. Yeah. So at each interval of time, sorry, like so you said like in 5 seconds I got like 4 or millimeter of water or 10 millimeter of water or whatever. And that's, by the way, an easy way to measure Q. Like if you want to measure Q like hydraulic flow, you can buy like maybe a $10,000 like flow meter. But the simple way is just like if you have a pocket and a stopwatch, you can just like if you have a pocket and you know like the size of this pocket, how much water you can fill this pocket up to, then you fill the pocket and see what is the time for filling out this bucket, and that will be your Q. So these are, I'm teaching you like cheap methods how to find like things, like to find Q, to find hydraulic conductivity. So hydraulic conductivity is cheap method to do it if you are in the construction site. Just use like what we showed like in grain size analysis, yeah? That will give you a quick value. And Q, just a bucket and a stopwatch. So basically here, so this is our equation here, K is equal to negative Q over area length times H, like the delta H. And then I can express Q as a volume over time. H, that's H1 minus A. In that case, actually, H here, that is like, should be like, because I have the negative sign here. So if I have the negative sign here, that should be H2 minus H1. And then the volume collected over time t. Here's a V, that would be the volume collected over time t. So here is an example. So a sample that is 30-meter long. So that, what does this 30-meter long means? That like my L is 30-meter long. The cross-sectional area is already given as 25. So this is my area. Yeah. Find the head difference was calculated as like so here the head difference is positive, so that's like h1 minus h2. So in that case you wouldn't need this negative sign here. Yeah, if the h is like negative, then you would need this negative sign. So like I mean, let me just do it, like let's do this one, and the head difference I will just put negative 5. See, so delta h, so I will say like delta h would be like negative 5 centimeter. Yeah, and the total 500 millimeter of water was collected in 5 minutes. So the volume is 50 millimeter, and the time was what, 5 minutes. Calculate K. So that is simple. So I'm not gonna solve it. Like here is like the equations that you have. Try to solve it, and like try to find the solution. So try to solve it, and it's just, it should be like a straightforward. Okay. Okay, so here this is a class exercise. Try to do this exercise. So here the constant head permeameter has a cross-sectional area. So the area is giving, the sample is, so L is giving, the length is giving, the head difference is giving. Yeah. So here, like you see, I'm not using the negative sign. Okay, and that's why you have like the head difference. So H is giving that's like 3.4 meter. The permeameter charge like Q is giving in 30 seconds, and time is giving. What is the hydraulic conductivity in centimeter per second and in feet per day? So try to calculate. This is a good exercise for you. It's a good exercise for the FE exam. It's a good exercise for also your exam, and it's a good exercise for your homework. So before you do the homework, try to do this example, and then in the homework you'll find like something similar to this. Yeah. So what is the hydraulic conductivity in centimeter per second and in feet per day? So try to, so you have everything. You have the V, you have the L, you have the A, you have this one, you have this one. Try to make some unit conversion. What is the intrinsic permeability if the hydraulic conductivity was measured at like this degree? So at this degree, the density of water is, this is the value, and the viscosity, like you are giving like this value. So I already gave you these value. You don't need to search for them. And remember, this is the permeability, like we can call this is a small k, like ki. And this is density, this is acceleration due to gravity, and this is viscosity. So try to calculate like, so basically like now you have k, you have this one, you have this one, so try to solve for this one. And then from the hydraulic conductivity value, name the type of the soil. So from this hydraulic conductivity value, whatever you get, like look at this scale and tell me like whether this is sand, whether this is gravel, whether this is silt, whether this is clay, like what this is. Yeah. Uh, so try to do this, and again, after you do it, check the solution downward in the notes. So like, let me show you the solution. So this is the solution. This is the correct answer, but don't look at it. I will like change the view now. So now get back here and start working on it. And after you work on it, then you check like that solutions that I showed you. Okay, so pause the video and please work on this now. These exercises will help you to solve your homework, will help you to get a good grade in the exam, and will help you in the FE exam also. Okay. Okay, the last message that I have for this video is the falling head permeameter. So we looked at the constant head permeameter. Well, the head difference is constant. And this used generally for non-cohesive sediments such as sand. For cohesive sediment with low conductivity, like clay or whatever, like a falling head permeameter is like generally used. And this one is a little bit different, like not a little bit different. It's like a different form, or like the other one was Darcy experiment. So the other one I was showing you how to conduct Darcy's experiment and to analyze the results. This is a little bit different. So here, what you will do is this is a falling head. So like this is a, let's say like this is your initial level, like at time 0, like this is head 0, like that's your head 0 at time 0. And then at time t, like here, so this is at time 0. And then like here at time like t, yeah, at time t, whatever is at time t, then you will have like a head value. And basically, the amount of water, so now you see here, so this is your water column, yeah, and this is like your sand column here. So this is like your water tube and the amount of water, and this is your sand tube or sand column. So the amount of water that will be discharged, so let's say you lost this amount of water, like Q here, like Q tube would be equal to the Q that's coming from here, because the water that, like, this water will go from here to here. Where will this water go? It will discharge from here. So basically, like Q tube is equal to Q of like your sand column here, like this sand column. And that's it. Yeah. The Q of the tube, like we know, like the flow equation here, Q is equal to velocity or like Q, like in the tube, that's like area. Yeah. So that would be like equal to area. And and the velocity, and the velocity would be like what, like your delta H over delta T, like the change in head, like how water, like the distance that this water will travel from here to here, for example. So that's delta H over delta T, because Q is like velocity time A. Yeah. Okay. And then because it's going like from high head to low head, so we can put like you can put like this negative sign here, and or you can put it on the other side. Okay, it depends like how you measure the delta H, but it doesn't matter. Okay, and then for the sample, what would be the Q here? That's like, so that's the Q for the tube. That would be like a negative area, like this area of the tube, yeah, time delta H, like how the distance over time, yeah. And for this one, that is like Darcy law, yeah. So Darcy law, we know that that would be like K, yeah, over area of this guy here, over like H. Uh, that would be like this, like head difference, like how much, the head difference uh, here over L, like the length, yeah. So that would be the, like this HE, like how much water basically like is flowing like through this one, yeah. And then like you can arrange the term, and then you will end up with this. So you can just like arrange the term in both sides, and then you will end up with this differential equation, ordinary differential equation. I'm not gonna solve this, so I want you to check, go back to your calculus, calc 2, I think, or calc 3 course, and learn how to solve this. That's easy. Like for example, if you integrate this guy, you will get a t. If you integrate this guy, you will get like len H, yeah, and then you evaluate it from H0 to H. Okay, So like try to solve this equation. Try to solve it in your own. I will show you the solution in the next slide. But before you move on, like pause the video, try to solve this and see if you'll get the final form. You should be able to do this because you took a calculus course. Yeah, you took 3 calculus course, calculus 1, calc 2, and calc 3. Okay. But anyway, so here is the equation. If you solve it, you will end up with something that looks like this. And then the rest is easy. Yeah. So you know, like, so here, that's like the t, so that h as, so here like this would be h as a function of t, that would be like your h node, and that would be the diameter of the tube, and that would be the diameter of your sand column. And then you collect different h value at different t value, and for each h value at the t value, then you will get like the k value. Yeah, you can plot this, for example, and as a straight line, and use regression. Okay, so falling head. So this is basically the here, this is the initial head, this is the final head. If you just want to the falling head, like you can do it like you can this be like head the final head, or it could be head at any time. It doesn't like the final head like final head at any time whenever uh, you stop. Time for the head fall and the this diameter of the tube, so the diameter of this tube and the inside diameter of the tube. Yeah, so this would be like this guy here, and this would be like this guy here. Okay. So again, this is like just another method, like, and you usually do this if you're doing sand or clay or something like this. Okay. Uh, so here permeability tests, they are so like, okay, now let's look at this. So these tests, they are suitable for low conductivity material, relatively inexpensive and more reliable than grain size analysis. So, and but more accurate K measurement depend on field tests. So that would be a future topic. So these ones, like you take the sample from the field, so you disturb the sample. So when you disturb the sample, that will have different properties than its in situ condition, and that's why like these lab method, like the number, like either constant head permeameter test or falling head permeameter test, both of them are useful, and but you only do them they can find also if you have low hydraulic conductivity materials, they can be effective in this. Low high hydraulic conductivity material, both they can be effective in this. But if you want something more accurate, then you do like a field measurements. Yeah. And before I talk about like field measurement, we'll have like whole module about this later on. But before I do field measurement, I just want you to practice this a little bit. And that's also, I think you might find this in the FE exam also. So I want you also to practice this a little bit. But yeah, but that's basically they are inexpensive. You can just go to the field, get as many samples, like run them in the lab. I think you will do one of these. I think it's the constant head permeameter test that you will do in just your technical engineering. This one is a little bit more time consuming, so you might not do this, like the other one might be easier. But anyway, before we move forward, and like I will just give you now like a little bit overview about like field method, just an overview, but we will have another lesson about this. I want you to solve these problems. So please pause the video. Here you have the equation, and just like read this, try. That would be good. I'm not gonna do it like I'm not gonna tell you like what is this, what is this. I want you to figure these out on your own, and want you to do the unit conversion on your own. So please do it. And after you do it, I will show you the answer. So pause the video, do it now, and get and check your answer, see if you did it correct or not. Okay. Okay, welcome back. So this is the answer of your problem. So if you answer this correctly, you should get something like this or something like this. And these are like these types of questions. This is more like an FE exam type of question. Yeah. FE will be like a multiple choice. Okay. Okay, so let's move forward. So we talked like the three method, like grain size analysis, falling head, constant head. These are like field, like lab method, but field method. This is an instrument which we have here at FGCU. This can measure like the saturated hydraulic conductivity. It's called like Satur. This is the name of this instrument by this company, and this is like a different philosophy. So this is not based on uh, falling head or constant head, like concepts that we know. This is based on something called this is based on something called like infiltration. So oops. So this is based on something called it measure like 3D infiltration. So that particular instrument is measure like 3D infiltration, like vertical and radial using infiltration models. And it preserves. So the big advantage of this one, this is like similar to the this is similar to the falling head and constant head, but not similar, but like same idea, same concept, except that this one you do in the field. So you measure the hydraulic conductivity K in the in situ condition, not disturbed soil, and so that is very like a neat equipment, and it preserve like the natural soil structure. So basically, like this what this instrument is moving, it's measuring like how easy water will move through the soil, and it will measure how easy water will flow through the soil through infiltrometer. So if water is not moving easily through the soil like you're doing clay, that is a test will take much longer time than if you're doing sand, for example. So you see this like silver cylinder here, like in this, like what you see here in this silver cylinder. This is called like an infiltration ring, and this sits on and you put this on the ground. Like so, in the field trip we will be doing this, and you put this like on the ground and hold water above the soil. So that will hold like the water above the soil, and this black case which you see here, like this black case this is control. This is like a control unit. It has a pump. So this control unit, it will pump the water into the ring and keep the water at two steady depths. So like it will keep the water at like two steady depths in the ring, one shallower and like one deeper. And by timing how fast water socks at each depth, so like at the shallow depth and the deeper depth, this instrument, this Satur instrument, it will figure out how easy water flows the soil when it's almost saturated, like the field hydraulic saturation condition, and how strongly the soil pull water. It can also measure like capillary actions at the full saturation. So basically, that's again like it's beyond the scope of this work to explain like the infiltration ring or infiltrometer test and like how to use this infiltrometer model. But that is something that you can use. Like think of this as something as constant head or falling head experiment, except that it is much easier to use. So now, like field method for measuring K depend on scale, aquifer type, like whether this is like a confined or unconfined, and like the focus, like whether you want like saturated or unsaturated. Usually for groundwater study we measure generally more interested in saturated condition. For soil scientists they might be interested also in unsaturated condition, because that's unsaturated condition you will learn about soil moisture, for example, which is important for plant nutrient uptake. So, and if you are also studying like flooding or things like that, also unsaturated condition would be also important to you. So on the field scale, like how do we measure hydraulic conductivity? So remember, all these are, you're just taking a small sample, like 20 centimeter, as you see in this previous example, by like 30 centimeter. All of them are small sample. But what we will do is like you can do like a pumping test that will take average K over large volume. So we will learn this in module. I think they have a module about well hydraulics, and then another module about field method where we'll learn how to we're not going to do a pumping test because that's very time consuming, but I will show you like step by step how to do it. And then we will use a software called Aquatisolve to analyze the pumping test result. And we will also solve it manually using some equation. Slug test, that's a cheap form of a pumping test. So this will give you like average K over large volume. This will give you like well scale, like a borehole scale measurement of. So that would be like a scale slightly larger than what you will do with an instrument like this or with like falling head or test, but much smaller than what you will do with a pumping test. Again, like if you understood pumping test, it should be easy for you to understand this one. Yeah. And if you want, like for your project, remember you can make your own project. So if you're in your own project, you want to do like slug test, we have the instrument for this. So that could be your own project. You can go to like FGC on campus or anywhere you like. We can give you like the instrument and then you can do like slug test. Pumping test, that would be a little bit more difficult. Tracer test, that's for understanding flow paths and if and effective K at like larger scale. So tracer test, it does not like from tracer test you learn about velocity and dispersivity, like the velocity and dispersivity, but you can infer the K value also from a tracer test. So these are like generally like the field task at the larger scale. So this is larger scale, this is larger scale, this is like slightly like smaller scale. Okay. Uh, Permeameter test, that's like in situ shallow unconfined aquifer for soil or soil layer. So permeameter test, that's like in situ unit. That is similar to the constant head and falling head. So constant head and falling head, these are permeameter tests. So you can do these tests in the field actually. Or infiltration test like unsaturated zone or recharge estimated, similar to the Satur equipment, where it can do like Satur equipment does not do the unsaturated, it does the saturated hydraulic conductivity when it's like fully saturated, so the soil like is fully saturated. Uh, so let me tell you something, like in this summer we will doing field work, and two university were doing it, like Florida State University and the FGCU. Florida State University, they were like doing this one, permeameter test, like for in situ. FGCU, we were doing like this one, infiltration test. Yeah. And so both are used, yeah, in the field to get some idea of hydraulic conductivity. But remember, this is only for shallow unconfined aquifer and topsoil layer. This you cannot go deep because you are just measuring like at the surface, yeah, hydraulic conductivity at the surface. So both of these, like this one and this one, would be just at a shallow level. Again, you can that would be like a good project idea. You can do a slug test, get like a measure like hydraulic conductivity value and compare it with like an infiltration test from like the two instruments that I just showed you. That would be like a good class project. Then geophysical methods, this is like electrical resistivity, like profiling or sounding or tomography or ground penetrating radar, and this is for like hydraulic property. This will not give you the hydraulic conductivity value, but that will give you an image. Like this is similar to, like, remember, for example, like you have a fractured bone. Like what do? Like you go to the doctor and the doctor will take an image, and then like this image will see under the skin and it will see through the bone. Like this geophysical image, again, that's very similar. We image through the subsurface. So we'll be imaged through the subsurface and it will give you, let me show you, like it will give you maybe an image that looks something like this, but without these values, yeah? Then to know these value, you can know these value either from a pumping test or from modeling, like you develop a model and then you can estimate this value, or from other method, like a slug test or a pumping test, or again, that could be another good project idea. We have like an electric, so that's like in the field trip, we will be doing ERT. So you can do ERT, and then this ERT will give you an image. So it will tell you here, you have this zone 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 here. Then you can do a slug test or permeameter test to find like the hydraulic, like the K here and the K value here. You're not going to be able to do it for the deeper unit, but at least you can do it for like this shallow unit. and it will be different because remember, like it is heterogeneous, so like you need to account for heterogeneity. So I will leave you maybe with this uh, I will leave you with this image so that you can see how nature could be very challenging for hydrologists, and see like just ponder about this image. Okay, so that's all for this video, and see you in the next video.